The organizers for inviting me to facility. As you said, there's nothing in this talk about charge exchange. However, X-rays are involved. Now, unfortunately, they're in the initial state rather than the final state. That's one difference. Also,
but you may start your talk from opposite side.
And the other similarity is that I want to start looking beyond just a single atomic center, dealing with the multi-atomic centered nature of some of these problems, the extension aspect of the talk. And what else did I want? Well, the other thing, of course, is that it's an overlap between atomic physics and astrophysics modeling. Let me also say I owe a lot to Alex, even though I've never collaborated with him formally. Out of his 750 papers, I am not a co-author on any of them, but I have visited here numerous times. I count that this is maybe my 6th ITAMP workshop, dating back to '96, and several in the audience were there. And just as importantly, I have visited here. I have taken advantage of the visiting scientist program. And that includes a year ago when this whole idea of absorption in solids was brought to my attention. I like single-centered problems myself, spherical symmetry, moving nuclei. But I was able to talk with several of you there, Randall and Julia, and Vasily first got me thinking about how to look at this problem. So, a lot of my career, indirectly is really due to Alex's formation of ITAMP, for which I'm very grateful. A brief outline. Not only do I want to go over atomic photoabsorption, which is the area I have focused on the most, and how it can be used to analyze X-ray spectra. And very recently we've looked at how to parameterize these atomic cross-sections. But as the second part of the talk, the ongoing work in progress here on the molecular aspects of photoabsorption, there are several interesting features. Oscillatory structure due to the interference between the multiple centers that I'll talk about with X-ray absorption fine structure considerations, a digression on some work we've done in photoabsorption and of endofullerene systems, and likewise, just as with the atomic, I'll look at some spectra there showing solid state features, and at the very end discuss multiple scattering theory a bit, which is, again, work in progress. I'm trying to minimize, knowing that this is a mixed audience, I'm trying to minimize the number of equations here, and so to give you a flavor of what exactly is involved in the atomic physics calculations, we rely on the well-established R-matrix theory of atomic collisions. It dates back to the Wigner nuclear physics days, but has been developed over decades, primarily as far as my work is concerned, with the Belfast group under Phil Burke. And the basic idea is that for a complicated electron-atom collision, which is the final state in photoionization, by the way, an atomic ion and an electron scattering away from that ion. The very complicated many-body problem is solved inside a so-called R-matrix sphere, the internal region. And there's a lot that goes into that, but at the end of the day, there's this analytical factor here known as the R matrix. It's a kind of generalized logarithmic derivative that allows one to project the inner region solution onto the outer region solutions, which are typically just Coulomb functions, or for a neutral target, just Bessel functions. Now, I'll talk a little more about the long-range wave function later when we get to multiple scattering theory, but that's the R matrix method, a well-developed technology. Just to point out that at the risk of seeming self-serving here, in that book there are 1,000. There's a point to this. There are 1,000 references there, so not to give the wrong idea. But much of my early work, when I was first a grad student at Auburn with Mitch Pizzol, and then interacting a lot with Francis Rochot and Nigel Badnell in particular, involved modifications to this standard coding in order to handle many additional physical effects which are required for photoabsorption in atoms, inner shell processes in particular. Now, I'll just point out a couple. Radiative damping was brought up by Peter yesterday, but the Auger damping is crucial for getting the correct shoulder broadening and the correct widths of inner shell resonances, and that in turn relies on a quantum defect formalism, which has been introduced in there. And more about the quantum defect later. In our latest work on oxygen, we found these two processes. One has to be careful in order to get orbital relaxation effects, which follow from inner shell vacancies. One had to be careful not to have these spurious pseudo-resonances pop up. Double continuum processes. This is a photon coming in, an inner shell electron being ejected, followed by the shake-up, if you like, the ejection of a second electron. That turns out to give something like 20% of the signal above the K-shell threshold. In any event, those were introduced here, and Phil Burke thought it was worthy of including in his long list of references much of this work. The other important thing is that back in 2000, I did K-shell photoabsorption of oxygen and neon. And where do we stand now? The very latest work, this has been in close collaboration with Javier. It's here today in the audience and here at CFA. Javier Garcia and Efrain Gatuz, who's a recent PhD student, just received his PhD, did a lot of the modeling here. And so we worked hard on getting the very latest, greatest oxygen photoabsorption cross-section and putting these into what they're now calling ISM apps, the latest absorption model for the interstellar medium. I am not an expert on these aspects here. You would have to ask Javier in particular more about this ISM apps package, but to show what all this looks like in a picture. Here is a comparison, if you like, of the theoretical photoabsorption cross-sections on the left. That's what we atomic physicists do, versus the observed X-ray spectra, using, these are, I believe, Chandra spectra. And just to talk you through this a little bit, in red here is the photo, being an atomic physicist, I like to plot versus energy, but in order to compare with the spectra, we're plotting here versus wavelength. So going from lower energy to higher energy, as we scan through, this is the K alpha, the 1s to 2p absorption in atomic oxygen, O1. As we go to higher energies, we get the K beta, etc., then an entire Rydberg series, and the above threshold photoionization of oxygen. And not only might there be neutral oxygen in the ISM, but we could also have singly or doubly ionized. So the green shows singly ionized, the blue doubly ionized. Same thing for neon. And if you look at the observed spectra, one sees going in that same, a large K alpha absorption of neutral oxygen, K alpha of singly ionized oxygen, a whole edge from the entire Rydberg series, if you like, some multiply ionized oxygen as well. And the same thing for neon. You note that the residuals are looking, pretty contained there, and that's the latest status of atomic absorption in the ISM theory and spectral modeling. What are a couple of the payoffs from this latest model? One is that this new spectral modeling has explained what had been suggested as some missing oxygen. A paper back in 2010 by Pinto et al. Had tried to fit the oxygen absorption spectrum with their available atomic data, and they were missing quite a lot in this little region, and which led them to suggest that perhaps there should be some molecular solid-state dust oxygen in the ISM, and that could explain why that the fit was so poor near the K edge. Again, this is the K edge of oxygen. I won't talk about any of that much, but, well, Javier's paper in 2011, using these data, were able to show that the previous Pinto et al. Study had been using incomplete atomic data. This is Brendan, McLaughlin, and Kate, when Brendan was here at ITAMP with Kate at 98, and they did the first stab at oxygen photoabsorption. However, there was not the Auger broadening I referred to very briefly, and as a result, they were not able to resolve the K edge of resonances. And there was absorption missing in their atomic cross sections. So that was the explanation, not that there was significant molecular solid state oxygen in the ISM, but rather the atomic, the neutral and ionic oxygen could explain the spectra that was observed. Another upshot was that, well, the latest modeling using just even Chandra data, but also looking at some calculations, including a very sophisticated, somewhat converged MCHF calculation, find a photon energy of the K alpha resonance at an energy that differs by more than half an EV from the latest, greatest laboratory measurements of Wayne Stolte et al. These are measured at the Advanced Light Source, and they swear by that number, and yet this Chandra data in particular has been calibrated using some well-known, I think, helium-like oxygen lines and some others, where if this is wrong, then then we don't know anything about helium-like oxygen either, and so it would just make all of this Chandra modeling inconsistent. So there's this outstanding discrepancy of more than half an EV between Chandra observations or calculations and the synchrotron experiments. Not only in neutral oxygen does this occur, but very recently I was in Orsay a year ago and talking with Jean-Marc Bizot, and this is still unpublished, they measured the K alpha, they were looking at photoabsorption in singly ionized oxygen. And likewise, there's that same difference of plus, one has to add half an EV to get from here to there. The same way, these Soleil measurements were more than half an EV lower than what Chandra was observing. So this might be considered a reverse engineering way to perhaps calibrate the experimental measurements using Chandra data. Okay. Well, I'd like to talk a bit about how we characterize atomic photoabsorption. And if one analyzes the actual R matrix output data, the scattering quantities, and applies multi-channel quantum defect theory, you can show that a complicated resonance series can really be parameterized by nothing. These numbers even come out of R matrix calculations. But as I chose neon as the simplest Rydberg series. One Rydberg series, furthermore, it doesn't even have an n equals 2 resonance. This is the 1s to 3p resonance, 1s to 4p, 5, 6, 7, infinity. This infinity is up to here, so the edge appears to be at a much lower energy, and the fit is beautiful. One can fit the theory or the experiment, which differs only by a bit. Another thing I'd like to point out is that we're guided by an analytical identity, the Thomas Reich-Kund sum rule, provided you have an accurate wave function. This can guide us when I want to extend this model to solid state environments, and using this can allow one to get a consistent description going from atomic to molecular photoabsorption. Same thing with oxygen. Here we have multiple Rydberg series. We also have the n equals 2 resonances, which are a little more tricky. But again, one can fit to the theory, and this also points out that the theoretical calculations, try as one may, there's usually ever so slight energy differences. One can take the model, the QDT parameterization, and adjust these numbers just a bit. Typically, the threshold energy is the one that the theory can't converge to the last six, we're talking about 500 EV and plus minus couple of tenths of an EV between theory and experiment, we can just adjust that model, go right through the experiment, essentially. Okay, so that's all atomic photoabsorption. What if we look at the spectrum more generally, such as in the iron L region or in the silicon K region, without even being an expert in atomic physics or spectral modeling, it's quite obvious that this neon or oxygen spectrum looks qualitatively much different from the iron or the silicon. Well, it's believed, it's generally believed that the neon we know is only atomic. The oxygen, this is still not an entirely settled issue, but the oxygen looks fairly atomic. Again, these are all Lorentzian profiles of Rydberg resonances. You look at iron and you just see these two almost threshold cusp type features, and this is what I first brought to Vasily's attention last year about what's going on here, and others had studied this quite a lot, but I wanted to try to understand how to view this, with an atomic perspective. Silicon as well, they appear to be primarily solid state, but the question is, well, could there be any solid state oxygen in the ISM? And likewise, could there be any atomic silicon or iron? And therefore, one would really like to have a model that included both. And that's the purpose here. And so that's where I want to go with the rest of this talk, is to extend to molecular and solid state environments. Using pictures, photoionization of an atom, we have a single center, photon in, electron out. The tilted side, if you tilt your head here, you can see the cross section, leaving aside the below threshold resonances. We have nothing. We hit a threshold. We get photoionization. Here, this signifies an emitted photoelectron wave, a single one propagating out. When we consider more than one atomic center, we can have scattering off that second center. You can also have absorption from the second center with the wave interfering with a wave from the first center. Any way you want to view it, again, this is just very cartoonish, but when we have a wave emanating from one center interfering with a wave from another, this is like your young two-slit interference or Bragg diffraction, one can get oscillations, constructive, destructive interference between two electron waves. And this is what I would like to try to focus on a little bit here, theoretically, if possible, with multiple scattering theory. But that's kind of the explanation. One major qualitative difference between the two, of course. And from a theorist point of view, what we're trying to do is go from this one, spherically symmetric atomic potential to, in the case of a diatomic molecule, two of these wells, or in the case of a solid, an infinite array of such atomic wells, which here I'm showing a bit of a muffin tin approach, and this is the way we want to go with the R matrix method, is to do an R matrix method at each atomic center, put those all together and get a wave function for solid state matter. Brief digression, because this is a theoretical experimental collaboration that we did recently, and it investigated a similar effect of the interference of electron waves from multiple scattering centers, and that is photoabsorption of endofullerene atoms. The particular case was that of inner shell photoabsorption, photoionization of the xenon atom. Xenon has a very large, what is known as a giant shaped resonance. This is a 4D electron absorbing a photon and emitting an epsilon F, an F wave, huge signal. Well, you put that, they're able to put that xenon atom inside a C60 fullerene molecule. And here again, this is just a schematic of what one might expect, is that this large shaped resonance signal might indicate some oscillatory structure. Many people have studied this system theoretically, okay, with varying levels of accuracy there, and but this is perhaps the definitive study on photoabsorption of xenon inside the experiment at the Advanced Light Source. It had to use ionized. They're using a beam, so strip an electron from a buckyball. And it's a little bit busy here. I'll show a second slide, but the calculations and the experiment without the buckyball are in very excellent agreement here. With the buckyball, the calculations, there are two separate calculations that are just changing the treatment of the fullerene a little bit to show that sensitivity, but both the calculations and the measurements indicate these oscillatory structures. As you recall, these same oscillations, let me just show on this next slide where we look at the difference. These oscillations are analogous to those XAFs, X-ray absorption fine structure oscillations that are seen in photoionization, X-ray absorption in solids. Okay. Now I'm kind of finishing up with the extensions of the quantum defect parameterization, going from atoms to, in this case, I'm just focusing on two different forms of molecular oxygen, O2, oxygen gas, and H2O, steam. I don't know if that's really the right way to, in any event, and what you can see is that the experimental oxygen can be fit quite well, as we saw already, with the QDT parameterization, which also fit the R matrix calculations, by the way, but the parameterization goes right through the atomic experiment. That same parameterization can be used for O2. What changes here? The threshold is lowered a bit. We know when we go from atomic to molecular, energies are going to do something. The threshold is lowered as we go from atomic to molecular oxygen. The quantum defect, which gives the position of the Rydberg resonances relative to threshold, that is being decreased a little bit. Aside from that, the exact same parameterization essentially goes through the O2 experiment. Well, one more time, we can look at H2O, and there the threshold is lowered even more. The quantum defect is decreased even more. You can get a fit. And this is not really just a fudging fit of sine waves. Remember, this is a established Rydberg series of resonances. What it should look like, regardless of the details of the calculation. Okay, so that's already we've got a model that has more than atomic oxygen in there. I just wanted to show from these same experiments, this is in applied physics, I believe material science studies, that the H2O in the gaseous form is this dark blue, still looks Rydberg-like. Well, once you go to water and ice, you get major qualitative differences. And it is this type of structure that we're really after trying to explain quantitatively, not from just a parameterization, but from real ab initio calculations. That is about where I'm at with, since thinking about this problem is, okay, how can one approach that? Very briefly, speaking of parameterization, the red indicates our matrix calculations for atomic iron. This is the iron L shell now, atomic iron, and from an R matrix calculation with some frame transformation, LS to JK. I don't want to kill you with the details too much, but this is the 2p to 3d absorption in iron, and there's a spin orbit splitting between the two 2p 3d resonances. There's an entire Rydberg series that's barely visible on this large energy scale, and then the double P 1/2 and 3/2 thresholds, or 3/2 and 1/2, and that is what an atomic prediction would give. The iron experiments show this, qualitatively different features. Notice they're not. These are Lorentzian in atomic, not Lorentzian anymore. Well, this experiment done in Berkeley, I know that, can be fit with a modified QDT parameterization as well. I don't want to say too much more about that, but one thing is, by putting these all on the same scale, we also show the background from an independent processes calculation or an experiment on solid iron, which really is only, even though they extended, I think these are just extrapolations down to threshold, but these are experimental measurements. And so it puts this other experiment on what should be the same absolute scale, need a factor of 2.3. That was a point I didn't make on the previous oxygen molecular absorption, is that by putting them all on the same graph, we're able to adjust in energies and or absolute scales to get a consistent picture between them all. And I wanted to point out, this is work done here at Harvard, I believe, by Julia Lee, looking at absorption in various forms of solid iron, and some quantitative differences between the absorption there. And so how could one try to think of what X-ray absorption would look like in, I probably don't know how to pronounce these, phthalate versus hematite, or any of these others? Well, that is where I'm going to conclude here for the most part, and what I've been working on now to extend atomic calculations to deal with multiple scattering centers is the basic theory of multiple scattering, which is a well-developed methodology used in material science, condensed matter. This is a book on multiple scattering. The essence is the following. When electrons propagate away from any given atomic center in a solid, because of the screening of other atoms, there is no Coulomb potential, and those electrons are basically they're in a potential, they satisfy the wave equation asymptotically. Okay? Therefore, they're Bessel functions along with a spherical harmonic. All right? If we try to build up a wave function that considers the multiple centers, this is a combination of atomic orbitals, if you like. If I try to build a simple wave function of a partial wave from one center plus a partial wave from another center, and I use this projection, since these generalized Bessel spherical functions are solutions of the wave equations, they are on either center. We can project a spherical wave from one center onto the other, and the coefficients that enter are the Bessel functions involving the separation between the two atoms. This red term here is the origin of all those X-ass oscillations, and this is what I'm working on now, is to try to go from ab initio, going from atomic to solid state using multiple scattering theory, and with that, and just let me show some preliminary calculations on silicon, but as I see the series up, and I'll just click from there to a brief mention of the many collaborators, including the astrophysics modelers, Javier here, and Efrain, and I have 4 grad students at Western, now 4, who are working on various aspects of that problem. And with that, I'll thank you for your attention.
Please, questions? Yes.
The cross-section you showed of oxygen by Stolte shows, there was one area that didn't fit, and I always remembered that he had that marked as being the oxygen, the O2 section.
Yeah.
So can you now fit that and say just how much O2 is in his system?
One could, right? I mean, here's O2 from an O2 experiment. Here's the little bit of O2 solution, and what they're trying to get is an O experiment. Now, by the way, notice we had to shift them differently. These 2 experiments, had a discrepancy of 0.2 eV, if you like. This has been shifted by an extra 0.2 in order to align. By the way, that's shifted to align with Chandra. That's shifted a little bit more so that those 2 features align. And anyway, go.
Right. So you could do. And the next question is, I thought those shifts were to deal with the theory not being able to get the energies quite right, or
that's always the case. But what I try to point out in that one slide is experiment and observation disagree.
Right.
So we're
right.
Putting our head.
Astrophysical gas is different than lab gas. That's.
You're going with Chandra, though, right?
No, we're going with the Chandra.
Okay.
That's
Okay, more questions? I have a question very simple. Could you show the ICES, experiment with
yeah, these.
Yeah. What is interesting, because we know that ICES, very kind of complicated structure, especially if it's small particles, they may be amorphous, they may be polycrystals, anything, in this case, how kind of reliable comparison if you don't know the structure? Because I see the spectrum different for different configuration. For iron, you show, yeah.
Right.
Yeah.
Yeah. That's,
Or should we average about all this grass, or how people may analyze it? Yeah, because I don't know really. In space ice, maybe on the top of the silicon grain. Yeah, it's maybe in comet it's independent particles. Yeah, it's flying. Yeah.
well, yeah, I don't know how to answer that exactly, but you can just look at the red and see that this is not the red. And so what one should
You
really,
see, I am
Brilliant, I know.
set in deep space. It's cold enough. Yeah.
are we observing just red, or is there something somewhere else here? And how one introduces all these different forms and everything, or whether that's even, at what point is it just improving your basis of fits in anything? I don't know the total answer on that. I was talking with Javier recently, but
Yeah, no, I'm impressed that shift really large, yeah, it's a 10 electron volt. I talk about generally between this red, yeah, and this blue, for example, yeah. And for future mission, yeah, which claims that they will have a better resolution, yeah, maybe it's possible even to see. I understand we don't have a liquid water, but this different configuration, maybe it's a sensitive method for diagnostic. I don't know. Yeah, okay.
Well, just to comment that the challenging thing is also that is not shown there is that you also have oxygen, single ionized and double ionized, and you're going to have pretty strong K alpha lines right there where the blue peaks are, for example, or where the O2, the molecular line is. So that complicates it even more.
Absolutely, but in comet, for example, you have it just ice mostly. Yeah,
that's true. Yeah.
In this case, maybe it's easy. Okay, thank you very much again. Yeah.